Hello, eighth graders. I'm glad we're here together again today. I'm Mr. Nichols, and today we're going to be talking about the conservation of matter and the states of matter. So we're going to dive right in. Um, I'm going to go ahead and share my screen with you really quickly. And so pause that just right there for a second so you can see it. And we're going to go current slide. There we go. That's better. Okay, so energy is involved in chemical and physical changes, as we've talked about before. Now, when there's a physical or chemical change that happens, the total amount of matter and the total amount of energy actually remains the same. This is what we call the laws of conservation of matter and energy. Now, the law of conservation of matter states that matter cannot be created or destroyed. So for example, if we wanted to make some water and we had some hydrogen and we had some oxygen, hydrogen and oxygen as molecules tend to pair up. So you'll have two oxygen atoms together in an oxygen molecule. And you'll have two hydrogens together in a hydrogen molecule. Now, to make water, everybody knows the formula for water, right? That's H2O. That means there's two hydrogens and one oxygen combined, okay? But we've got molecules of two oxygens. We can't just combine one of them and say the other one disappears. We cannot destroy matter, okay? Nor can we simply create matter either. So what do? We actually end up with two hydrogen molecules with an atom each, two atoms each. There's two hydrogens for a hydrogen molecule, two hydrogens for a hydrogen molecule, and an oxygen molecule has two atoms of oxygen. So when they recombine, you get two molecules of H2O, okay? A total of four hydrogen molecules on this side and two oxygen molecules. And when we recombine to make water, we still have four hydrogen molecules, or four hydrogen atoms, excuse me, and two oxygen atoms, which are being recombined to form water molecules, two hydrogens and an oxygen in each molecule. So we neither created nor destroyed any of the atoms that were necessary to make water. Now, the same is true of energy too. We're not going to focus too much on energy today, but energy cannot be created or destroyed. It can, however, change from one form to another. And of course, matter can also change form. It can change phase, it can change all sorts of things, but it cannot be created or destroyed. So when we talk about changing matter, oftentimes we're talking about phase changes. And an important physical property of matter is the ability to change phase. Now, the three most common phases of matter are solids, liquids, and gases. And there's actually other phases as well. There is plasma, and there is, depending on who you ask, there's actually quite a few other phases. But we're going to focus on solid, liquid, and gas right now. And we will talk about plasma a little bit later on, so hang on. Water can exist as a solid, a liquid, or a gas, okay? And most substances exist in these various different phases. Changes in phase are also physical changes. So water, as you see here, solid water is what we call ice, but it's still water. Liquid water is water, and gaseous water is still water. We didn't change anything, okay? So it's a physical change. If we had changed something, it would have been a chemical change. So, for example, physical properties of ice and steam are very different, but they're still both water. There's no change in the chemical nature of the two substances. Solid gold and liquid gold are exactly the same chemically, even though the phases, solid and liquid, are different. So here we have a picture that shows us how the various phases of matter differ. So solid, it holds its shape, and there is a fixed volume. So I have a glass here, okay, cup, and I'm going to put a solid in it. And by putting that solid in there, it maintains its shape. Getting a little bit of glare from the computer, sorry. It maintains its shape, and it, okay, it has a fixed volume. It does not increase in volume in any way, shape, or form. Okay, so my solid is right there in the glass. You can see it. A liquid takes the shape of the container. It has a free surface and it has a fixed volume. So here we have a liquid. Now our liquid happens to be water. And we are going to take and add some little food coloring to our water. It's hopefully a little easier to see. Mix that up a little bit. Okay. And water, as everyone knows, is a liquid. By definition, it takes the shape of the container. So it's going to have a specific shape depending on what the container is, okay? And it has a specific volume. It's not going to expand or contract. It has a certain volume. Our last group is gas. And we're going to take a cup and we're going to scoop up some gas. There we go. We've got some air in there. We've scooped up some air. It again takes the shape of the container, but it fills up the entire container, doesn't it? There's air all the way up to the top. In fact, there's air that's going in and out the whole time. It has the volume of the container, it has the shape of the container, and as you can see, it totally filled up that container. All right. I'm gonna tip it too far, I don't want to lose it. Okay. So these can go from one phase to another. For example, a phase change might include melting, freezing, condensing, evaporating, and sublimating. Now, melting occurs when a solid changes into a liquid. Now, whether that's ice turning into water or solid piece of iron turning into liquid iron, it's still called melting, okay? Now, to get a solid piece of iron to turn into liquid iron requires a lot of heat. And we don't normally think of that as, you know, iron melting into liquid iron, but we call it melting. Freezing occurs when a liquid becomes a solid. Again, this could be water turning into ice, or it could be liquid iron turning back into solid iron. And again, this would be at a temperature so hot you wouldn't want to touch it, okay? But we call it freezing, okay? Condensation involves a gas becoming a liquid. So for example, if you were out on a hot summer day and you had your glass of lemonade and you notice the water on the outside, that's condensing, okay? That's water from the air that has touched it, because it's so much colder, it goes from a gas to a liquid, and it gathers on the side of the glass and trickles down the side. Evaporation is when a liquid, again, there's enough energy in these molecules that occasionally some of it will escape the container. Okay, it'll get out of the container and it becomes a gas. This is evaporation. Sublimation is when a solid goes from a solid directly to a gas. We don't have very many examples of this, but if you've ever played with dry ice, when you put dry ice in, just setting dry ice out, you will see it, if you put it in water, for example, you'll see it start to bubble. It's boiling, okay? It's not hot. It's actually very, very, very cold to the touch, but for dry ice, it's actually boiling. It's going from a solid directly to a gas. And phase changes require either the addition of heat, such as in melting, evaporation, and sublimation, or the removal or subtracting of heat, such as condensing or freezing. Okay. All right. Let's go full screen of that. So let's talk a little bit about these three states of matter. You've just walked home on one of the coldest days of the year, okay? So imagine walking home. A fire is blazing in the fireplace, and there is a pot of water on the stove to make hot chocolate. The water begins to bubble. Steam rises from the pot. You make your hot chocolate, but it is too hot to drink. You don't want to wait for it to cool down. So you add an ice cube. You watch the ice cube melt in the hot liquid until the drink is just the right temperature. Then you enjoy your hot drink while warming yourself by the fire. The scene described has examples of three of the most familiar states of matter: solid, liquid, and gas. The states of matter are physical forms in which the substance can exist. For example, water commonly exists in three states of matter: as ice, as water, and as steam, right? Matter is made up of tiny particles called atoms and molecules. These particles are too small to see without a very powerful microscope. Atoms and molecules are always in motion and are always bumping into each other. The particles interact with each other, and the way they interact with each other helps determine the state of matter. So, solid, liquid, and gas. Particles in a solid do not move fast enough to overcome the strong attraction between them. So they are close together and they vibrate in place, okay? Particles in liquid move fast enough to overcome some of the attraction between them. The particles are close enough, but can slide past each other, so they're not stuck. And particles in a gas move fast enough to overcome almost all the attraction between them. The particles are far apart and move independently of one another. So imagine dropping something into a glass, okay? Would anything change to the shape or size of that object? Okay. What if we put it in a larger glass? Would it change then? Of course not. Solids have a definite shape and a definite volume. And even in a bottle, that object is going to keep its original shape and volume. Now, the shape and volume stay the same no matter what size you drop it in. because it is a solid. And as a solid, that state of matter is described as a shape and a volume. The particles of a substance in a solid state are very close together. They attract to one another. And the attraction between them is stronger than the attraction between the particles of the same substance in a liquid or gaseous state. The particles that in the solid move, but they do not move fast enough to overcome that attraction. So you don't see any motion in a solid. Therefore, each particle is locked in place by all the other particles around it. Now, there are actually two types of solids. Now, this part you might not recognize or remember. And so you'll want to make sure that you take some notes while we're talking. And if I talk too fast, feel free to stop the video, move it back, and listen to it again, okay? So there's two types of solids. One is crystalline, and the other is amorphous. Crystalline solids have very orderly, three-dimensional arrangement of particles. The particles of crystalline solids are in a repeating pattern of rows. So things like iron, diamonds, and ice are examples of crystalline solids. Amorphous solids are made of particles that do not have a special arrangement. So each particle is in one place, but the particles are not arranged in a pattern. Okay? Examples of amorphous include things like glass, rubber, and wax. Each one of those would be amorphous solids. Now, it is very important to remember that a crystalline solid holds their shape, but amorphous solids do not. That's a misconception. Okay, so it's very important to understand this misconception that it's not just that the crystallines that hold their shapes. Amorphous solids also hold their shapes. It is true that particles in an amorphous solid are not arranged in a definite pattern, but each particle remains in position relative to the surrounding particles. So it is still a solid, it still holds its shape, it's just not like a crystal. Okay, let's talk liquids. Liquids, okay, like our liquid here. What do you think would change, let's see, about orange juice? If we were to pour it from a can into a glass, what would change? Would the volume of the juice be different? Would the taste of it change? Some people think the taste changes. The only thing that would change when the juice is poured into the glass is the shape of the container, okay? It's just the shape of the container. The shape changes because the juice is a liquid, and liquid is in a state of matter that has a definite volume, but it takes the shape of the container, okay? It takes the shape of the container. Although liquids change shape, they do not easily change volume. Now, does that mean they can change volume? Yeah, a little bit. They can. A can of juice contains a certain volume of liquid. That volume stays the same if you pour the juice into a larger container or into a smaller one. A special property of liquids is surface tension. Surface tension is the force that acts on particles on the surface of the liquid. Surface tension causes some liquids to form spherical drops, like beads of water on a plant in the morning. You go outside and you see dew on your grass. There's a little bead of water on there. It's formed a little ball, a little sphere. Okay, that's because it has surface tension. The outside part holds it together in that shape. So it's kind of a fun thing that water can do with its surface tension. Different liquids have different surface tensions. For example, gasoline has a very low surface tension. So when it forms a drop, the drops are kind of flat, very flat. Water, higher surface tension, and you can get a nice sphere out of it. Another property of liquids is viscosity. That's kind of a fun word to say. Go ahead and say that with me. Viscosity. Viscosity. Viscosity is a liquid's resistance to flow. Now, usually the stronger the attraction between molecules of a liquid, the more viscous the liquid is. For example, honey flows more slowly than water. So honey has a higher viscosity than water because it flows more slowly. Now, what's our third state? Oh yes, gases. Okay. And we are basically just swimming in gases. We've got nitrogen and oxygen and all sorts of gases floating around us. Okay. Would you believe that one small tank of helium can fill almost 700 balloons? That's a lot. How is that possible? I mean, the tank might only stand, 4 feet tall, might be this big around, but it can fill about 700 balloons? I mean, the volume of the tank is equal to only about 5 big balloons, okay? The answer has to do with helium's state of matter. Helium is a gas, and as a gas, the state of matter has no definite shape or volume. The particles of a gas move quickly so they can break away completely from one another. And the particles of gas have less attraction between them than do particles of the same substance in the solid or liquid state. The amount of empty space between gas particles can change. So the particles of helium in a balloon are farther apart than the particles of helium in the tank. We'd say that the particles of helium in the tank are under pressure. They're squished together, okay? And as that helium escapes the tank and goes into the balloon, it is no longer under all of that pressure and it expands. It makes the balloon expand too. Now we're going to talk about some of the special laws of gases later on. Not today, not even this week, but we will be soon, all right? Let's talk a little bit about those changes of state. We gave a little bit of a hint before. We want to talk about it too, because they can be tricky. And speaking of tricky, this next story talks about that. It can be tricky to eat a frozen juice bar outside on a hot day. In just minutes, the juice bar will start to melt. Soon, the solid juice bar becomes a liquid mess. As the juice bar melts, it goes through a state of change, a change of state. In this section, you're going to learn about the four changes of state, okay? And a fifth change that is just incredible, all right? So the four changes of state, I'm getting some help from my little ones. Sorry about that. A change of state is when we go from one physical form to another, solid, liquid, or gas. And all changes of state are physical changes, okay? So if you go from a solid to a liquid, that's a physical change. A liquid to a gas is a physical change. It's not a chemical change. We're not changing substances. The particles of a substance move differently depending on the state of the substance. The particles also have different amounts of energy when the substance is in different states. For example, okay, Particles in liquid water have more energy than particles in ice. And particles in steam have more energy than particles in liquid water. So to change a substance from one state to another, you must either add or remove energy, like we stated at the beginning in the introduction. Melting is when we move from a solid to a liquid. And this takes place when you add energy, okay, to the solid. It melts. We call it melting when we go from a solid to a liquid. Doesn't matter what the substance is, okay? For a solid to melt, particles must overcome some of their attractions to each other. When a solid is at its melting point, any energy added to it is used to overcome these attractions. Melting is an endothermic change because energy is gained by the substance as the state changes. Okay? Freezing is the opposite. We're going from a liquid to a solid. So when we're freezing, we're removing. For a liquid to freeze, the attractions between the particles must overcome the motion of the particles. The motion is where we find the energy, okay? It's kinetic energy, it's bumping into each other. Imagine that a liquid is at the freezing point. By removing energy, by slowing those particles down, it'll go from a liquid to a solid. And this is known as an exothermic change. Exothermic because the heat energy is leaving the water and it's going from a liquid to a solid. Okay. Evaporation is when we go from a liquid to a gas. For example, if you've ever ironed something, you wanted your clothes to be nice and crisp and not wrinkly. Usually you'll spray a little bit of water on there and you run the iron over it and there's a steam that comes off. Well, that liquid is boiling and becoming a vapor, becoming a gas. Evaporation is the change of a liquid to a gas. And so we add energy to that liquid so that the molecules start moving so fast that they take off and they become part of a more gaseous form. Okay. Now, the difference between boiling and evaporation. Both of them are liquids becoming a gas, right? There's actually a little bit of a difference in science. Boiling occurs in a liquid at its boiling point. What's water's boiling point? It's 212 degrees Fahrenheit. In Celsius, does anybody know what it is in Celsius? Celsius is kind of convenient. It's at 100 degrees Celsius, okay, is the boiling point of water. Like that's the definition of Celsius. And as part of its definition, 0 degrees is its freezing point in Celsius. So it goes from 0 to 100. In Fahrenheit, we go from 32 degrees Fahrenheit to 212 degrees Fahrenheit. Oh, I mean, for those of us who use Fahrenheit, a little harder to remember. So boiling occurs when a liquid is at its boiling point. As energy is added to the liquid, particles throughout the liquid move faster. When they move fast enough, they break away from other particles and they evaporate and become a gas. This is boiling. Now, evaporation, just plain old evaporation. Evaporation can also occur in a liquid below boiling point. Some particles on the surface of the liquid move fast enough to break away from the particles around them, and they become a gas. So it happens faster if we raise the temperature, but it continues to happen even if the temperature is much lower. So water in the ocean, even though it's not boiling, it can evaporate. And that's why we've got the water cycle. Not talking about the water cycle today, though. Let's move on. Condensation is when gas becomes a liquid. We talked about that with a glass of lemonade on a hot day. That lemonade is nice and cold, and the air around it has water vapor in it, which when it comes in contact with the glass is turned back into a liquid, okay? For gas to become a liquid, large numbers of particles must clump together. Particles clump together when the attraction between them overcomes their motion. So the movement of the particles as a gas is much faster, but they get together and they clump together, and then that motion slows down and it's no longer gas, now it's a liquid. Because energy is removed, condensation is what we call an exothermic change. So the heat from that particle of water actually leaves it and it cools down. So it's an exothermic change. Now, those are 4 changes. I told you there was a 5th that was kind of interesting. That's called sublimation. That's when we go from a solid to a gas, and it doesn't stop at the liquid form. There's no liquid in it. Okay, it just goes straight from a solid to a gas. No liquid in between. Okay. For a solid to change directly into gas, the particles of the substance must move directly from being very, very tightly packed, okay, to being spread very far apart. So the attractions between the particles must be completely overcome. The substance must gain energy for the particles to overcome their attractions. Thus, sublimation is it endothermic or exothermic? It's endothermic because we have to add energy into it, right? We add energy in, goes from a solid to a gas. Well, that energy makes those particles move from very slowly vibrating to very fast and excited and all over the place, okay? Sublimation. All right, so that's as far as we're gonna go today. I hope you enjoyed our lesson, and stay healthy and stay happy. We'll see you guys soon. Take care.